Okay, hello everyone. Thanks for showing up early in the morning. So we're gonna just continue where we left off last time, and talk a little, continue talking about the flow control a bit, and then go into some of the subcomponents that of the network, and and then in the end we'll look at some of the evaluations that we were doing to kind of put everything together. So just as a quick reminder of like where we left off last time, is we talked about the flit buffered flow control. Remember, flow control could have been done at the packet level and the flit level, and we talked about kind of inefficiencies in doing it at the packet level because you kind of have to reserve the resources for the whole duration of the packet, the buffers, the channels, the switch traversal, and that creates a lot of buffering overhead and a lot of inefficiency in the system because channel gets blocked while the whole packet goes through and things like that. And so the next kind of better thing to do is to chunk the packet in flits and then let those mingle through, basically both through all the shared resources, through the buffers, through the channels, so that you can let others pass through if you are blocked somewhere down the line, right? And so we talked about the wormhole routing, which kind of lets you send the first flit even though the rest gets blocked. However, you still have a problem basically that if you're downstream blocked, then and this buffer is full, you're going to essentially have to clog this channel or leave it idle because you can't add another flit here to the switch because this first flit or however many flits are already in the buffer cannot advance forward, because for the flit to advance forward, it has to get access granted to traverse the switch and then also have a reservation in the downstream channel and the downstream buffer. And the reason for all this is that you don't want to lose these flits. If you have to lose these flits along the way, there is another layer of the network that you have to add that takes this into account and resends either the flit or resends the overall packet or the message, right? And that ends up increasing the latency significantly. And that in these types of networks, which are really memory semantic networks, where you really want to kind of get as quickly as possible to fetch a word or a cache line somewhere across the chip, you don't want to have that. The same principle is also even in the chassis level that I showed you earlier, where let's call it small distributed compute system. You're still not using networking protocols to go out in a full TCP/IP stack. You are using these shallower protocols and relying on reasonably reliable delivery between these compute nodes so that you don't increase the latency, right? So a solution for this to kind of not necessarily help this guy who's blocked anyway, but let others pass through the switch, is to introduce virtual channels. And what that means, if you think a little bit about it, it's kind of adding finer granularity to the paths that you can traverse through the switch. So what we're doing here is at every input port, we categorize the incoming thing by where it wants to go, right? So we can open up a few more paths. For example, if you come here and you can distinguish between flits A and B, well, A wants to actually go this way, and that channel is available, and the downstream buffer is available. B, however, is blocked, right? So if we had only a single buffer with kind of first in, first out, B would be blocking A, so you wouldn't be able, A would not be able to traverse. But we kind of parallelize here. So instead of one deep buffer, we make several shallower buffers, and then A can actually traverse the switch in this direction and move to channel Q. And now both channel P and Q are basically utilized, while the downstream for B is blocked, but that's fine. That's just a property of what happened in the network. But we're effectively now using this channel P, whereas in the previous case, both P and Q were blocked, right? And here we're using them. So the network utilization increases. And if you remember these throughput versus latency curves, flow control was kind of shrinking that compared to the zero load. And so now we're kind of enabling better utilization, so higher throughput, so moving to the right side of that curve. Now, this does complicate a little bit the architecture of the router itself. There's no free lunch here because the router now has to decide for each port among the virtual channels who goes where. Right? So the arbitration in the router gets a bit more complex, but we can take that hit with more efficient logic scaling, different routing algorithms and things like that. Still a good price to pay for increasing the overall network utilization and throughput. So an example of these virtual channels and some examples of what happens inside the router as it's looking at these two virtual channels, A and B, and deciding who to let go. Because there's an additional arbitration there that has to happen. So these inputs, A and B, basically compete for bandwidth in the channels kind of flip by flip basis, right? So you have A head, B head, and then the payloads. So one arbitration, which we'll call fair, would, let's say, let kind of ping pong between the two. So go head, A head, B head, A1, B1, etc. And so what that results in is basically kind of interleaving of the flits on the kind of going traversing the switch. So we call that fair arbitration because kind of both make it at the same time. But notice that another strategy, which is, let's say, winner take all. So even though A and B heads arrived at the same time, you let one of them take it and go through, then that one basically makes it earlier through the switch, and then B basically makes it a bit later. There's no throughput penalty here. Both make it together at the same unit of time, but you are reducing the average latency, right? Because A now gets completely done way earlier. This guy that gets done at the same time, if you average the latencies, you actually win, right? So it's kind of like a interesting thing that something you're kind of trading fairness for average latency in the system. And those are all the decisions people need to do when they design these routers and scheduling algorithms. And there's a whole literature on that, from, you know, fair arbitration, winner take all, round robin, then islip, all sorts of schedulers that kind of can do these things. And also implementing these schedules. This is not a software scheduler, so you can quickly change it. This is a baked in the hardware. It's basically a priority decoder or some sort of things like that. And it has real implications on how fast the router can actually work. And we'll touch on that in the next several slides downstream. As you're architecting the router, you want to know in how many cycles you'll actually be able to traverse a router. And these types of decisions and arbitration can take some amount of time there. So you want to make sure that happens really fast. But if it has to happen very fast, it can be really complex, meaning you can't take all sorts of variables into account. It has to be some simplistic scheme of determining arbitration, yet satisfying the overall application goals. Okay, so here's a little bit of the anatomy of the virtual channel router. So as we already talked about, we kind of the finest thing you can use, and it's pretty much everywhere nowadays if you look at on-chip networks as well as the networks in these like distributed systems like I showed you, DGX, right, NV switches, they all have this virtual channel architecture because it gives you the most flexibility in increasing the throughput while minimizing the latency and congestion. So let's say in this case, we have per port, we have two virtual channels, right? And then you have a switch here. And then we also have this virtual channel, is the channel buffer at the output. It's very important in every system, whenever you have a resource that is contended for, you got to buffer it at the input and the output. And that will allow you the most flexibility basically in traversing that resource with highest utilization. And those are the kinds of things that are happening here. So we'll walk through this kind of the mechanism. How do you actually get the reservation to traverse? But some definitions are, you have the virtual channel, you have the virtual channel status, means is it allocated or not? I'm going to use it or not, and to which output virtual channel it's going. Okay. That's used when we're making arbitration here in the switch, which input virtual channel to let through the switch. We'll use that tag to say, okay, where do you want to go? How many other people want to go to that port? And then do some arbitration among those to select the winner, right, for that flit cycle. Then we have the switch. We're going to talk about how you can physically implement this crossbar itself. And then the trade-off that you have is to decide how deep these buffers need to be. You, of course, have a limited amount of SRAM on the chip that you can dedicate to the chip, the crossbar, the logic, all that will be kind of another size, but you have a certain limitation on the amount of SRAM you can put. You need to make decisions. Do you make one long VC, or for that same amount of memory, you make 2 shorter VCs, or 4 even shorter VCs, right? And of course, this will depend on the radix of the switch as well. The more VCs you have, like if you had the same number of VCs as the output ports, that's the best, right? Because each one can then go separately. But in a 16 radix router, it's 16 VCs, right? And each has to have a certain depth that we're actually going to cover what the requirement is for. So you kind of have to tailor these things appropriately. The wrong choice of the buffer depth can significantly affect your flow, right? So this is kind of, I hate this thing, it won't go away. Okay, so we're going to go through this line that says basically that each channel, so the depth, how many flits can I store per virtual channel, has to have some relationship to the round trip latency on the channel, right? And actually the throughput of that channel. If you think about it, and we're going to go through that example, but if you think about it, I'm the sender. So I'm sending stuff. It has to reach across the channel. And I have to get something back telling me, like a credit that we talked about, telling me, yeah, it's been received, stored, and now I can send another one, right? So the throughput times the round trip latency on the channel is really what determines the overall number of bits you need to store in order not to lose anything. That's in the networking called Little's law, and applies to kind of anything in the networking. You just have, the fatter the pipe you have or the channel, and the longer the latency, the more you have to store to be able on either end to not lose anything, right? So that's kind of the point. So if you think about how this is scaling, the faster the network I want to have, and the longer the latency I have, if I'm building a bigger chip and the space between routers is bigger, the more buffering I need. So my routers get more complex, right? So this is kind of all tied together. So this is kind of the mechanism that I just mentioned, right? So you're basically exchanging the credits between the kind of the output, the outputs of one switch across the channel and the input of VC of the next switch, right? And it matters what happens across this channel. So as you're sending the bits, so you're sending stuff, decrementing your credits, and then at some point in time, you have to, as you decremented your credits to 0, you've now transferred both flits, right? You started with 2. Now you have to receive a credit back in order to be able to transmit the next one. That means that the head already had to kind of leave and make one empty slot in the input buffer so that you can actually now populate. So this credit closely tracks what's the availability in the downstream buffer so that you can actually send stuff, right? So if we look at this timing diagram here, you're looking essentially at the period between the two, when the credit was sent, a little bit of processing, and the flit traverses, assuming that the processing, meaning incrementing of the credit or decrementing, is not that time consuming, you end up essentially with the round trip time that's needed for you to send another flit across, right? In the case that the buffer downstream is full, once it empties, that's the whole procedure that has to happen. Credit, flit, and now you have sent actual flit, right? So now that's why the depth of the downstream buffer has to be this round trip, or F is kind of the depth in the number of flits, is the round trip latency times the bandwidth, of course, divided by the length of the flit in bits. So round trip latency times the bandwidth gives you the total number of bits that are sent. You divide them by the length of the flit and you get F. So this is kind of a small application of Little's law on this one channel. Little's law in general applies even for end-to-end networks at any protocol level. Wherever you are buffering stuff to be able to recover it from the other end, you have to take this sort of calculation into account. It's also a very nice way to tell someone they're bullshitting you, because you can quickly calculate these things for any protocol level and see if their architecture makes any sense, right? And often people talk about, let's say, significantly expanding the bandwidth and making the system beautiful. Well, if they're not shortening the latency, then they're putting heavy burden on the buffering in the system, and usually it's unsustainable, right? I just don't have enough SRAM to do all that, or the energy of that SRAM is going to go through the roof, and there's all sorts of trade-offs. So you can quickly analyze these things and say whether this system makes sense or not, right? Okay, these were kind of the networking basics, and in the references in the kind of some of the last slides, I have some kind of interesting pointers for you to probe further. One of the most important ones, and it's actually available online, you can just Google it and download the whole book. It's Bill Daly's Principles of Interconnects, Daly and Tulls. It's a really good book. I recommend highly to kind of flip through it. And we kind of based all these definitions and architectures on that. So if you want to kind of learn the computer networking basics, I'm not talking about TCP, IP, and the whole Ethernet stuff, but compute networks, this is the best book I know. So we're going to talk now about the building blocks. Now that we kind of understand the topologies and some throughput definitions, flow control, these layers that are used, how do we go about building the channels and the routers? What are the options? How do we go from a logical implementation to something that's physical, right? In this class, we want to build hardware, not just architect. So to do that, kind of have to understand a little bit of the building block costs, right? So, and of course, in any technology, you can do this exercise. This was done a long time ago in 90 nanometer archaic technology, but it gives you some idea about what's going on. So for example, what we're doing here is looking at the whole mesh network, right? And trying to see, because what we really care about is energy per cycle for the whole system. How much energy do you burn in the mesh versus the routers alone, right? For some certain throughput that we want in the system, as we increase kind of the router to router link width. So as we're, remember the formula for bisection bandwidth, right? As we're increasing the router link width, you're basically getting more and more throughput in the system, right? It does affect your router complexity. It also affects your channel energy because you just have more wires that are toggling, right? And so we wanted to see like where's the cross point or roughly the balance between the router and kind of the mesh. So by the mesh, we're talking here about kind of channel energy, right? So you basically see that kind of mesh energy kind of scales linearly. Okay, we're basically increasing the number of channels, but the router energy goes quadratically, right, with the number of channels. So you have to be careful how you're sizing up the two things. Now, if you look at kind of what's happening inside the router, this is, for example, router area breakdowns. The blue and the red are the crossbars. So 32-bit versus 64. Okay, you have doubling. So it's kind of linear in the number of bits you're traversing, but it's going to be quadratic in terms of the ports, right? So what we're showing here is the number of ports, right? Because you have kind of a two-dimensional switching thing that happens inside the router itself. And then, of course, measuring some SRAM area, because remember, we have to do both output virtual channels buffers and input virtual channel buffers. So it's useful to understand how much of the overall area of the switch goes to the actual switching and how much it goes to the buffering, right? So you see that buffering is kind of comparable in the large number of ports. You're essentially almost kind of a wash, and then it goes a little bit more for the larger crossbar here on top. Looking at the channels, you have to, depending on the network topology, traverse a certain distance on the chip. This could be a millimeter if we're talking about mesh, where your core is about a millimeter or a few millimeters going to the next core. If you're talking about C mesh, you're concentrating several cores per router, then you have to go longer distance, at least the size of the core, which is then a few millimeters or 3 millimeters. And then as you do claw, you have to do even longer routes, so that we had to go maybe half the chip or the whole perimeter of the chip, depending on where we place the middle stages in the system. And so you have a few choices how you want to do that. Turns out if you're going these longer distances, you can't actually make it in a single cycle. If you just do a repeated wire, and you want to have a reasonable energy efficiency, so you have like a 10 out of 4, maybe 5, depending what you're doing and what your target clock frequency is, then you may not end up traversing in a single cycle, and you don't want to necessarily do kind of wave pipelining where you're just sending bits and they arrive 2 cycles later. So then kind of the conservative way of doing it is to sizing the repeaters and just putting the flops wherever the cycle ends, right? So this is like your whole duration of the traversal of the cycle, right? Well, that adds energy, adds latency in terms of real clock cycles going through. So there's just some examples that we played with that shows you, okay, to traverse, if you have a millimeter or a 10 millimeter distance, right? You have number of pipeline segments you want to go through, and basically your energy increases. If you look at, let's say, 10 millimeter distance, right? You're essentially optimal somewhere around 5 pipeline segments, right? Because if you chunk it into smaller chunks, you're kind of wasting resources because you're adding more flops. If you try to make it faster, meaning with less segments, you're essentially going to be doing fan out of 2 or something like that crazy on the repeaters, and then you're not going to be able to, your energy is going to go up, right? Because you're basically pushing the frequency on that shorter chunk. Of course, that also has to do, the whole design space is wire width, repeater size, repeater spacing, what's the energy of your flops. You can write a little optimization routine to do this in the proper way, given the constraints on what's the trunk of the area that you can dedicate to the wires between the 2 routers, etc. Right? Another thing that people played, we played, about a decade ago with these things, Valeo was a switch company that tried to build large radix switches where you have long wires that traverse the switch, not just the channel itself, right? We're going to talk about the crossbars as well. And then you had these like interconnects, like rings that span the multiple cores and things like that. So people were very interested at some point in time. How do I traverse, let's say, a 10 millimeter, 10 millimeter distance on a chip, which is heavy RC? It's just basically a stringed RC model. So it's very dispersive. You have significant channel attenuation here. Can you do it without repeaters faster, right? So they brought in equalization techniques from high-speed links, chip to chip, to try to see how can I make a simple high-pass filter here to kind of, instead of sending a single bit, I kind of send something and I send kind of a negative voltage value following, and that kind of cancels out the low pass filtering effect of the channel. And then maybe I added a little bit of decision feedback equalization that just cancels kind of the tail based on the previous, what was the value of the previous bit. I don't want to kind of go too much into these equalization techniques, that's like on another class, but people were trying to do some, let's call it mixed signal things that are not really digital necessarily. And I'll show you there's some benefits to that. You can basically signal across without adding inverter delays. So you're very close to basically speed of light, quote, quote, on that segment. So you can shrink the latency. Because your signal swing is smaller across, you also can save energy, depending how smart you are building the transmit and the receive side, how complex that equalization is. But people have shown that you can do very simple tricks there with a few flip-flops on the receive and transmit end and achieve these kinds of things. It also goes to say that, you know, if you're implementing something like this, you don't really have to run these repeaters at full voltage, right? Depends on what clock cycle you chose to signal at. All the voltage scaling, low swing kind of things that we apply to logic, we could apply to these repeaters as well to be able to reduce the overall wire energy. We could build sans-amp-based flip-flops that recover the low swing into high swing. So there's kind of like a whole spectrum of techniques you can use to lower the energy on the channel for given throughput requirements, right? It's not just repeaters versus equalize, but there's low swing, etc. Right? So those are the kinds of things people are considering on these things. Of course, one thing to keep in mind, these are all high SNR situations. You don't want to be losing bits because your swing is too small, and now the all sorts of power supply noise, thermal noise, all of that stuff comes in, and with some probability it ruins your bit. Right? This has to be like 1E minus 18, 1E minus 20 type of reliability. So it's still a very, very high signal to noise ratio, even though you're lowering the swing. So you always have to keep that in mind. That's why people look at estimating what's the supply noise they're getting on these things, putting regulators and all sorts of things to minimize that so they can shrink the swing and recover the energy. So this is a little bit of the comparison. When you have these types of channels, some energy is proportional to data. Right? That's what switches through the repeater. Right? But for example, clock energy on the flop that we had is not data proportional. It happens at twice the frequency, right? The data density on average is 25%, switching, clock is 50, right? So that is something you have to keep in mind when you are comparing these things, because there will be a portion of energy that's not dependent on the network utilization. And then there will be a portion of energy that is dependent on data utilization. And as your data network utilization goes low, then this one that doesn't depend on it kind of sticks out. So your network doesn't scale well with utilization, right? That's also some consideration people want to have, because people in general want to have an idle network burning zero power, right? And then a full throttle network burning in the max power. But if you have a lot of flops and clocks and everything in the network, that's not necessarily going to happen unless you end up gating those flops. That's another technique you can use, but it requires kind of state control and things like that. So here we're showing basically just the repeater-based energy, and you have a difference between kind of how much repeaters and wires cost versus how much the flops cost. The fixed energy is basically just clocking those flops. And then on the equalized, you have a much smaller energy. You see basically that the reason why you win on the equalized is because most of your energy is in the wires and the repeaters. The fixed energy of some number of flops, whether they're equalizing or distributed across several flops, is less, right? So it's kind of comparable. Okay, so that's a little bit about the channels and kind of the options you have there. I would say that, you know, people don't really build equalized links today, especially because it's a risk of this bit error rate and losing the packets. But what people do is look very carefully at what swing you want to have on those wires if you really want to have a low power optimized network on chip, especially for longer routes. So talking about the router architecture, we're going to go into some of these building blocks and see how we're going to implement them. So if we look at the input unit, there are a few states you have to keep track of, right? There's a global state, there is the route, which route you're actually taking, what's the output VC that you're targeting, and then pointers, credit count, and things like that. Credit count goes back to the input. In the output VC, you have, again, kind of the global state of the VC, the input VC that has gotten access to that output unit, and also the credit count, because you want to make sure that you basically give some notion of how free that output VC is back when you're doing the allocation. Okay. So you can't do all these operations within a router within a single cycle. Right? There are multiple stages at which you need to be making some decisions. And so I'll walk you through some of the optimizations that you can do depending on what architecture you select. So for example, the first one is basically several things you need to do. You need to do route computation. Remember, we had the measured order routing, for example, deterministic, we had tag. And so you have to figure out when ping comes in, on which port it's going, right? So you need to, and then go ask for the status of those resources. Can you actually make it, right? So that's basically the route computation stage. Then there's the virtual channel allocation stage, meaning, do we have the virtual channel to go into to be able to traverse the switch? Then there's the switch allocation. Is the switch wire crossing from input 1 to output 2 available, right? Or someone else also wants to go to output 2, in which case I can't make it there, right? And then there's the actual switch traversal. If switch is big, as you will see, you have, depending on the implementation of the switch, it's either going to be a wire delay or it's going to be some logic delay if you're maxing things out and then deciding, right? So you need to dedicate some time to each one of these stages. So let's say each one of these takes roughly a cycle, right? Whatever that means. A cycle could be multiple clock cycles, depends on the implementation. And then you have to basically do the route computation for the head flit, because that is what contains the route information, the tag or the dimensions. And then you need to do virtual channel allocation for, again, the head flit kind of signals that everything else is coming. And then the switch and switch traversal, you can do just those two basically for all the body flits and the tail flit. Okay. Now, if in any one of these steps, which has some potential contention, meaning some other people are trying to get that resource, there's a potential that you will stall. So you won't be able to advance. That's why we have all these buffers in the system, so they can keep, right? And so you could have a situation where, the head flit does the route computation, right? And then it has to wait for the virtual channel to be allocated, because now that it knows where it's going, it sees that there's some resource that's not being available, so it needs to wait until that resource becomes available, and then it can do the other steps, right? For packet B, for example, as it's coming in, it can do on another virtual channel, it can come and go through because its head flit has already reserved all the stuff, right? So it basically has a free pass. Okay. And then, of course, once the head flit A does the virtual channel allocation and traverses itself, you can basically get the body flit to go through, right? The important thing also here is that to notice that we are overlapping some stages, right? While the head flit, for example, is making the switch traversal, the body flit can already get into switch allocation stage, right? Because these two don't overlap. One has been granted pass, they go, the other one is into that computation stage, bidding for the channels across the switch, just like with every other virtual channel. Okay. So, yeah.
Is there a chance, the previous slide, is there a chance that while the packet B is being transmitted, the VC is dropped and changed back to, like, the VC allocation is changed to some other state?
You don't want to drop the packet, right? You're just not granting it for the flit. You're not granting it to advance, and you're holding it in the input VC. And you holding it in the input VC kind of pushes back on the downstream or the upstream channel to not send another thing, because if it did send, your buffer would overflow, right? So that's what the flow control does for you. And in credit-based, you wouldn't be able to do it because you're not sending it a credit, so you're not allowing it to transmit, right? And there are many other ways you can do the flow control, but credit-based is kind of one that we went through, right? It very explicitly tells it not to send, right? There are others where you can send and set an expiration timer for an acknowledgement, right? And if you don't get an acknowledgement, it's been lost. So you just keep bumping, but then you have to have very deep buffer yourself to be able to contain all the possible losses, right? It again has to do with the throughput and round trip. So you can't avoid Little's law any way you try, right? It's just that there are those different mechanisms that, for example, don't want to do the credit increment, decrement. They just rather send a whole bunch of stuff and then get axed for that, right? I mean, you see that example in traditional networking as well, where you just get a stream of acts depending on the depth of the buffers. Yeah. Now, just like in computer architecture, when you have branches, anything that requires decisions and arbitration, you can do speculation, right? And so you can basically try to overlap the virtual channel allocation with switch allocation, because you're still holding the thing. So you're just doing two allocations at the same time. And if it doesn't go through, okay, you still hold the buffer, right? So you can kind of overlap these two cycles. You can also try to kind of overlap the switch traversal as well and try to jam as many things as possible. And notice that this is only happening kind of in the head flit. That's where you really get the improvement, because for the body flits, you don't have the virtual channel allocation. You're just doing switch and allocation and switch traversal. So depending on the size of your switch, if you can fit switch allocation and traversal in a single cycle, you can try to do that and just hold your buffer until you actually make it all the way through, right? There is another thing you can do, and that's essentially to save on the route computation. Because you can do the route computation for the next guy. Right? So when you receive stuff, someone's already computed for you on which of your outputs the packet should go. And that information is embedded in the head flit. And then what you do is you do it for your neighbor, right? For the next guy. That way you can pack the route computation in the same first cycle as the virtual channel allocation, right? And it's kind of a little bit, you're kind of paying it forward, so to speak, right? So that's kind of a strategy how you can try for the head flit to pack everything in a single cycle. It's kind of a very aggressive way of doing it, but it's possible if you have cooperation across the whole network where your upstream switch is doing the route computation for you, and then you're doing it for the downstream switch. Now, in the crossbar switches, so we talked about the input buffers, the output buffers. The thing is that if you just have, for example, input buffers, right, and they're bidding for a resource, and this, of course, depends on the nature of the traffic, but we analyze it for, let's say, uniform random. It's easy to do statistically, like on a closed form solution. You can actually derive this formula that I'm putting here, which gives you theta is the overall effective throughput through the switch, depending on the S0, which is the speed up in the output buffer, and SI, which is essentially the speed up in the input buffer. And so what happens here is, well, let's think about it this way, in case the number of ports. So what happens is the more ports I have, right, the higher the likelihood is for me to basically hit, for all these guys to hit a certain same output resource, right? So without the speed up, basically I will have some capacity or chance of collisions. And since I don't have any buffering here, if these two guys bid for the same output, only one of them can make it, right? But if I have some way of speeding up, so I get the requests from both, and then I do first one, and then I do immediately the second one after that. So I have an internal speed up in deciding who goes between these two inputs. I can actually improve the chances of traversing the switch. Right? And so that's what's happening here with, let's say in this example, with no speed up, you only get 68% of the capacity of the switch, right? So you lose 32%. But if you have two input speed up, you're kind of 10% away from the capacity, right? And of course, this depends on the radix, the number of ports of the switch, and the speed up factor that you can dial in. So that will depend on your technology. How fast can you process these arbitrations and assign kind of the switch allocation and traversal. And then you have you can do the same thing at the output, because as you are bidding for the switch allocation, it depends on how many things you can fit in the output buffers, right? So you can do basically the output speed up or both the input and the output speed up. And then the thing, okay, theoretically 137% of capacity, obviously you can't do that much because you actually have physical wires traversing, right? But it just shows you that this is no longer an issue, that you can actually make it across, and probabilistic collisions are not going to affect you, right? So how do we put all of that together? We did a little study kind of, okay, how do these parameters affect the router complexity, the cycle time, and things like that? And some decisions to make is, okay, what is your flit size, right? how many ports you're going to have. What is the size of your overall system that determines basically the destination address. So if you look at your head flit, you know, you have to have a destination address, and then you have to have flit type buff identifier, and then these are kind of the data bits that you can transmit. So in this case, we kind of have the buffer for 4 messages that you can or 4 flits that you can keep in any of the input VCs. And then from the input ports, you have to go to the state to read off the state of each of the input ports. And based on that state, which is, it's a request, where do I want to go to each of the output ports? You enter that into the round robin arbiter. And these round robin arbiters essentially run on a per port. So that, let's say per output port, I'm running a round robin. I get requests from all the input ports. I see which ones are for that output port. And then I run a priority encoder or decoder to basically tell me, okay, let's say in this round, port number 1 has the priority, right? And then everyone else is basically lower priority in certain descending order. And I'm looking at which port gate wanted to go to that output port, right? Whoever is the first on that priority list goes. Next time around, I decrement the priority by 1, so everyone shifts. So now it's a little bit fairer to the next person who actually wanted to go to the same place, right? And there, round robin is the simplest because you just need an incrementer for the state. But there are many other schemes that are a little bit more complex that give you, let's say, better fairness under non-uniform traffic conditions and things like that. And then finally, you have to kind of transition the crossbar and then also buffer things on the outside. Or in this case, we're just doing input VCs, and we're just essentially having registers at the other side to latch the data that traverses. So it's really just like a pipeline stage. So now, how do I build the crossbar, right? Well, a simple way to do it is just to have 2 dimensions of wires, right? Inputs, outputs, and I have tri-state control on each one of these. It's basically a distributed multiplexer, right? So if I want to go from input 1 to output 1, I'll just turn this one on. It will connect the 2 wires, but everything else is, all of these guys are going to be tri-stated. So I only drive this, right? It sounds very nice and compact, but it actually is not. And the reason is that the moment you have to add the tri-state to kind of bridge the wires, you have to go down from any metal layer via down, allocate some transistor area via up, vias, contacts, all that adds space. And you can't that compactly route it because you're kind of introducing these pockets in the whole grid of the routes of the wires, right? And so it's kind of a, and if you want the tool to do it, it becomes even bigger mess because the tool doesn't really understand tri-states and what to do with them. So people have done these custom slices. Like, for example, if you look at this slice, it kind of repeats, right? So if you design very nicely the floor plan of one slice, you can kind of stage it. But it ends up being complex. The other thing is that notice that the, even though these are tri-stated, of course, the drain capacitance adds the load to the line, right? So you have this increasing load depending on the size of your switch, right? And if you want to put in a repeater there to buffer the wire, now you have even more density you have to deal with because now you need some space for the repeater, right? To put it down, remember there's another wire, let's say sitting here. Right? There's a bunch of wires in one direction and a bunch of wires in the other direction. So these in general are hard, even though they look like a nice solution. The one that is prevalent, I would say today, and I'll show you some evaluations, but people have figured it out, is the max crossbar. or we call this an output multiplexed crossbar. So what really happens here is that from each input, you basically fan out the wire to all the outputs. Right? And then at the output, you have a mux tree. In this case, it's basically, let's say, a 5-to-1 mux. Right? It will be essentially any number of, you have, if your radix is n, it will be n-to-1 mux at each input. And of course, you can build that as a tree. The nice thing about this is that you can let the place and route tool deal with this portion over here, right? And also deal with optimizing the mux logic. So it's very nice. You can also pipeline it much more easily. And with repeaters, you can pipeline the muxes. So it's a much nicer thing to kind of, for the tools to work with to achieve the density, because they can determine kind of the area for the wire routes and repeaters. And then they have a whole another section for logic. And that section is localized per port. And that's kind of what's important, right? Because then you can locally optimize that logic without having to have it be distributed like in a tri-state fashion. So let's say an example system. 64 tiles, 8 by 8, let's say 1 gigahertz frequency. We want to have a 512 bits is the size of the message. And then we have 4 messages per input, so 2480 bits or per input port, right? And then let's say we have a router aspect ratio of 1, 5, 8, or 12 ports, right? What does it mean, router aspect ratios? How are we floor planning this router? How does it look like? And also, what's the width of the flits with which we want to handle the message? So we're playing with 32, 64, 128. And then 2 different types of implementing the crossbar, right? So it's about design space of about 18 routers. And now the nice thing is with Chisel and all these things, you can kind of code this up in a single generator and just spit out and put it through the tools and see what happens. This was all kind of done a little bit earlier with parameterized Verilog and stuff like that. But let's see, for this system of 64 cores, if we went with a 5x5 router, right? Remember, that router is single router per core, right? So this basically shows each core, their ordering, and kind of the architecture of the router. So you have the 5 ports, each has a 16 word of 128 bits. That's basically the queue. Because remember, we calculated what's the total length of the message we need to save based on our credit of flow control, right? So you have 5 SRAMs, each per port, and then you have to figure out how to do the kind of the placement and routing of this. On an 8x8, you're kind of grouping, this is a CMash architecture, right? Where you have 4 cores using 1 router. And then you have fatter wires coming out because you have to kind of match the throughput on each port of all the 4 cores that are coming in. And so this now requires 8 SRAMs to fit in the same router. 12 by 12, this is further concentrating things to 12 cores, talking to a single router, and then doing meshes in between. And so then you can kind of take a look at how things look like in terms of area. Obviously, with port width of bits, if we go, things should be kind of growing linearly, right? Because we're just increasing the port width, we're not increasing the radix. Right? But you have these overheads of SRAM that's already been there, right? So you have to, that doesn't change with the port width in bits. It's fixed amount of SRAM. The crossbar for given port number is also the same, just scales the number of wires, right? So this kind of shows you that. And this really gives you the difference between the matrix and the, so if you look at 12 by 12 mux and 12 by 12 matrix, for larger number of wires per port, you start getting very significant difference in area because of this, what we talked about. If you have matrix or a tri-state based crossbar, you have to allocate this area for tri-states, potentially for the repeaters across, and that just eats up in the wire density. With output mux crossbar, you can kind of optimize that, run denser wires, and then locally stage your logic so that you can optimize the overall area. So you can kind of see that, but you can kind of see it more dominantly for wider buses. Right? If you have only a few wires running across per port, then it's not such a big deal. You still have the area available to put the logic. Right. Then power per port, basically here we're kind of also showing different types of traffic patterns. So you can see that essentially there's some variation depending whether you're running uniform random or some other traffic pattern in the system. And you also see kind of a significant power difference between the mux and the matrix. Right. Simply because remember, with matrix, all your drain capacitances of all the ports load the wire. On the other hand, you just have a wire that reaches some number of ports, right? So you can optimize it better. We do see, however, that if you go to 12, you basically get the increase in the power just by the number of ports, and it kind of the separation of these kind of grows. So it's kind of a quadratic increase in the power as well as the area as you're going to the larger number of ports, and that's one of the reasons why you don't really go above 16 ports on these types of switches. Even NV switch, I think, is 18 ports. In terms of the router power, really what dominates is basically the crossbar power and then the SRAM. But even this was like 90 nanometer, wires are really the ones that take a lot of energy, right? Where you can scale SRAM, you really can't scale the wire delays. You need to insert repeaters and do all sorts of things there. So that's why people, I mentioned Valeo back in the day, they had, we're talking about 256 radix or 128 radix switches, right? We're here talking about 18. As you can imagine, for 256, that wiring complexity becomes much bigger. You have something that's the order of a radical size switch, right? So you have to traverse basically centimeters worth of wiring. And there are all sorts of techniques, low swing, whatever you can do to minimize basically this energy is really what makes the router power efficient. Another interesting way to look at this, which is actually the true way of looking at the router costs, right? So far, I've been showing you just how things grow with the number of ports, right? But remember that while things grow with the number of ports, I have fewer of these in the system. If I want to connect 64 tiles, if I do 5-port router, I need 64 of them. If I do CMesh, I basically need 16 of them, right? Etc. So if you increase the concentration, yes, that one router becomes bigger, but I have fewer of them in the system. So the question is, what is the overall area and power overhead of the routing infrastructure compared to the area of the cores? Because the sum of the whole area of the cores is really my total compute. And I want to know what is my total networking and how these two balance together. Right? That's really what matters, not how big a single router is. Right? So this kind of shows you essentially area fraction versus the ports or versus the, let's say, the concentration level, right? So if we have, and then for different bit widths. Let's say if we just look at the max based ones, right? You actually see that it's not a good choice to do a 5-port router because the area fraction compared to the cores is actually higher. Right? So my area requirements on the whole die, if the whole compute die is area limited for yield reasons, then if I have these 5-port routers, I'm actually hurting the computation. And remember, I'm also hurting the latency of the whole thing because a full mesh 4x4 is actually going to have the longest latency, right? And so those are some choices that you have to do once you have this type of area evaluation, or let's call it a router generator. You can run this quickly and see for your technology, how does this curve look like, right? And then you see that it kind of flattens out here between 8 and 12 ports. So in terms of area, I'm okay with 8, and I know with power-wise, I'm actually better with 8, right? So I can do that kind of calculation. And this is kind of the effects of, these are the effects of concentration that we're just mentioning. So if you take a look here, the concentration works well for small number of ports, right? What we're showing here is basically going from, or let's just focus on the max design because that's what we're going to do. You're going from, you have 5-port to 8-port. So you see that with 8-port, your overall area is 0.37. The overall area of all the 5-port is 1.16. So you would obviously in this situation choose the 8-port, right? And then if you look at widening the channel, you also win here at 128 bits versus 64. And then if you want to go in concentration, even a little bit higher from 8 to 12, that still works. It works for Mux because our Mux has a much more efficient crossbar implementation, right? For Matrix, you see that that already doesn't work. Because remember, Matrix was this tri-state, so my crossbar implementation was not as efficient, so my area was bigger. And then going from 8 to 12 ports, your area quadratically grows because as a number of ports. So you pretty quickly lose that advantage of concentration because you're linearly decreasing the kind of the number of routers while you're quadratically increasing the router size. And so in Mux that works because you have a better efficiency in implementing that crossbar. But it kind of holds only up to a radix of 12, right? And these kind of reasonable channel widths of like 64. If you try to implement wider channel widths, of course, the switch area also increases, so it doesn't pay off. Right? But it's kind of a sweet spot here. And I mean, you can see that the power is also lower, right? But in this case, it starts becoming higher. So here, for example, it will be a trade-off. What matters more to you, power or area or latency of the network? So you have to run an application and see what really matters. Right. Now, doing these things it takes time to code up something, push it all the way through the flow, and do it. Now that we have Hammer as kind of an interesting tool that you'll be using to try to automate some of these tasks, as well as chisel-based generators, these things, stitching these pipelines of design exploration is easier, but it's not still super easy, right? So people have been looking at tools that can do more lighter weight type exploration that still is rooted in some reasonable estimation of what the area, what power would be, right? And so Orion 2 was one of the tools, or Orion 1, 2, that Lishan's group, Princeton did. And you could see, like, if you look at throughout time, how Orion 1 compares to Orion 2, it's totally, Orion was totally bogus, for example, compared to place and route, right? Because it was done at a time where certain things, you could ignore certain things in the technology. And then as you use it several years later, let's say the wiring becomes much more prominent, so repeaters, so it doesn't do good estimation of that, or in distributed logic, and you immediately have a problem pulling all that up to some higher level, right? But I mean, you see kind of that for smaller routers, it tracks well. And once you get to bigger routers where you essentially don't have, you don't have a good estimate of the wiring, or you essentially start getting reasonable errors there. Okay, we're doing on time. This section is kind of more of an evaluation, just to show you, like, recap some of these principles that we talked about. How would you floor plan things, your multiple choices and things like that, and we can go through that pretty quickly. So we talked about different topologies and how claw networks allow you to have this flexibility in the middle stage to be able to route and kind of even out the traffic patterns for, or contention for various traffic patterns. And that allows you to have not the fastest possible latency, but uniform latency that's more robust to different types of applications you're going to run. So if what matters to you is predictability, regardless of what you're running, this is a good type of network to use. If you, however, want to have the network run really fast on some subset of applications, but you don't care how slow it runs on others, then you don't want to use this type of network, because this one really tries to balance everything out and doesn't achieve its best, but it achieves kind of a uniform type distribution. But for general purpose machines, it's kind of nice because you actually want that predictability. And if you look at the data centers, all the backend networks are claw, or basically FAT3, which is a folded claw network, right? So it's very popular in a lot of places, especially for this. On chip, it's kind of challenging to do because of these long wires that are required to reach the middle routers, right? Because in this example, what we have is, remember, we have the starting router, the end router, and the middle, right? And the starting and end, okay, it makes sense to kind of be local to the group. If we have 8 array, 2 fly, 3 fly, right? We have 8 cores per input router, right? And on the output router is the same 8 cores. So it makes sense for those 2 routers to be the same and locally organized, let's say here, for this group of 8 cores. Now the question becomes, where do I put the middle router? Right? I have 8 of them in a system of 64 tiles. I could either locate them in each one of these groups, but then remember, from this group, I need to reach the center of each group. So it's a lot of wires going all over the chip, right? And some of the longest routes are, let's say, from here to here. That's like two edges of the chip worth of wire length. If your chip is a centimeter square, which is actually a small chip, you end up with 2 centimeters worth of wire you'd have to traverse, hopefully in a cycle. And that's not that easy, right? So another strategy is to put things here in the middle. So this way, all of your routes are basically the same, right? All the routes are essentially half of one edge of the chip, right? Which is 4 times better than in the worst case of the previous floor plan, right? The previous floor plan has the advantage that some wires are very short, right? From one group to another, from this one to this one, from here to here. But the longest one is really what hurts you, right? And you want to have the same latency in traversing the channel from one router to another. Otherwise, it messes up the whole buffering credits. You would have to have different buffering on every router, but you only want to design one router, right? You don't want to design 10 different flavors of the router, right? So this type of these types of things matter a lot when you're making these design decisions. And especially this is really purely a floor plan choice. It has nothing to do with the logical mapping of the claw network that we did. So this will be something you have to do in Hammer, right? Code up where you want things and have some sort of estimation, how long of a wire you're getting, how does that impact the cycle time, etc. Right? So we, of course, what the cycle time is, where it's placed, all that has to feed back into a simulator. So the simulator can tell you what are these throughput versus latency curves, because we want to take all the effects into the account. We don't want to just do the back on the envelope zero low latency analysis, right? And ideal throughput. So we're kind of comparing the C meshes with claw networks, and then for different traffic conditions. So you have like uniform random, two different types of semi-global, kind of global traffic conditions, and then a local traffic, right, within the task. See how this all stacks up. This is kind of, these traffic patterns for networking people are like a proxy for the application, right? For example, if you look at FFT, right? FFT really is an all-to-all type of communication, but it's kind of a permutation based, right? If you want to fully parallelize to all the tiles. Other applications will have different patterns, and with these, you're really trying to emulate kind of what these applications will be doing. Now, there's also kind of a way of thinking about, one thing is what's the application pattern, traffic pattern. Another one is how do I do my grouping in a C mesh, right? For example, if I have two tiles that are grouped, is it best to group them locally, or do I group them kind of across the chip, right? If I do an 8 tiles partition, how do I do that? Do I have them all grouped like this, or do I have them as a group like this, right? These choices have obvious power implications, right? Here, I would have to put my router somewhere here so that all of these blues can reach me with shortest distance. That's my subnet, right? But those wires are longer than in this case, right? But then that router could talk very quickly to the router of the other partition. So I may not have that much congestion or power there. Here, I would have to go from this partition to this, or like in the worst case, from this partition to that partition, right? So all of these things kind of matter, and you need to kind of bring them in. One kind of increases the channel cost from the core to the router. Another one increases the channel cost from router to router. And you need to kind of be able to balance these out, right? So this is kind of the some of the results, for example, you can get. You have latency per in the number of cycles and offered bandwidth. Remember, offered bandwidth was how much can the core inject without saturating the network. If you start saturating the network, your latency goes to infinity. Right? You just can't get anything through. Why? Because the credit-based flow control doesn't let you actually send the bit. Right? And so starting from a mesh, if you look at kind of the C mesh, it essentially has lower zero load latency, and then essentially also even with flow control basically allows you to have on various patterns have generally lower latency than the mesh. And then the claw, it kind of averages out things. This is kind of the phenomenon I've been talking about. You see that in the worst case, in the best case, mesh can do better, right? But that best case is kind of a local pattern, which is P8C. So it's a local communication within one group of 8. But the moment you go to uniform random, you're basically at 20. Okay, claw is the same. If you go to other patterns, which are kind of very localized point to point across that are more than the average of the mesh, you end up with very bad mesh latency, right? And actually very bad throughput, because you're communicating in pairs across a large section. You're traversing many routers, a lot of collisions, and your overall throughput basically suffers. While the claw is able to balance this out with this randomized middle stage routing, so you get a much tighter distribution across any traffic pattern. And of course, the effective throughput is almost double compared to what you get on the mesh for some of the kind of bad, let's call them bad traffic patterns or malicious traffic patterns, right? So that's something that's an advantage of the claw network. And then, you can kind of see it also in terms of the power. If you look at, for example, repeater insertion, you can see these effects of concentrating the mesh. Simply, there's a balance between the number of wire channels and the number of routers. This is another way to show that even with increasing the offered bandwidth, which means increasing the bits per channel, right, that the router can handle, you basically get better with the C mesh than the mesh, because mesh has all these overheads, many more routers per total system installed, and each router has some fixed capacity. Right. I think we can you can kind of go through these. Hopefully, Eric has posted the slides, so you can take a look at these. But it kind of gives you an idea overall of where, for example, the repeated versus the equalized, you're getting roughly about 2x savings on the channel power on the equalized, simply because of the lower swing that you're using, right? And then kind of what's interesting is to look at kind of the overall power breakdowns. Where are things going, right? So if you look at C mesh versus flat fly versus claw, flat fly is really a butterfly. So it's a two-stage but folded back, right? That's why it's called flat fly. And if you look at kind of the repeater-based ones, you see that router power actually decreases as you go to claw, simply because you have more cores attaching to, let's say, moderate complexity router, right? Whereas in the mesh case, and even C mesh, you have many more routers around, right? In claw, we're using an 8-port. In C mesh X2, we're also using an 8-port, but there's more of them. And so you have essentially power saving on the router, and then but you pay on the channel fixed power. Remember, there's flops that are clocking along the channel, and then there's the data dependent power that's larger. This is simply because our wire routes are longer than on the C mesh. What you get in return for that is this uniformity in traffic and higher effective throughput in the system for a whole range of applications. So you kind of have to trade off these two things. And then you can kind of do these similar kind of studies. Remember, we talked about virtual channels and their impact, right? So for the same amount of total memory on the root router, I can decide, remember, to do either one big or 2 or 4 channels that are shallower. All of these things give you kind of some trade-off between the overall achievable throughput for a given pattern and the latency. So here you see basically that with 4 VCs, I actually have, for all of the traffic patterns that were chosen here, I have some improvement in the overall saturation throughput in the application. So if you have enough memory to partition it, best to partition it to as many VCs as you can. But you have to keep in mind is what's your channel routing distance, and are you satisfying that credit-based flow control law? Yeah, and these are some of the charts you can go and take a look. Let me see if there's yeah. One other thing that I want to quickly mention to you just in the last minute is that these are a lot of very complex kind of things you can stitch together, and there are some tools here that you can actually use. Decent and Delphi are kind of two tools that are kind of more recent. Orion is another one, and there's some network simulators there that you can play with. One other thing that's very important in analysis, and it kind of looks like zero low latency, is something that you may have heard about in architecture classes, which is roofline type analysis. And that's a very simple thing, how you can estimate any such system like this, or memory interconnect network, etc. So just to sketch it quickly for you, if you have effective flops per second, and here you have computational requirement, and this will be in, let's say, flop per byte, right? If I can do many flops per 1 byte of data, right, I don't need any interface, right? So that line here would be just computation. 5 teraflops for whatever is installed, how fast your ALUs can work, right? At some point in time, you hit a number which basically corresponds to what's the speed of your memory interface, right? Or how fast you can run the data. And then your computation is entirely data limited. Basically, if my application requires more bytes per flop than this cutoff, then I'm only going to do as much computation as many bytes I get, right? Regardless of what was installed. So for any system, be it 64 tile, 8 tile on chip, or being a VGX box, you can go and quickly from their data sheets figure out what this is. From the interface specifications for the network, you can figure out what this line is. And you can basically call bullshit on anyone who tells you that they're running fast or not, because they will be bound by this curve. They can't do better than this curve, right? Really with latency, with contention, bit error rates, all sorts of these artifacts, they will actually do something like this in practice, but they can't do better than this line, right? It's just another way to kind of check people. Okay, thanks, see you in the next lecture. There's some bibliography here, so you can check out, and I already mentioned Dali's book. You can Google it and kind of get it as a PDF.